Good day, everyone. My name is Dasmi Maharaj, and I'm a master's student in the Hydrometallurgy and Minerals to Metals group at the University of Cape Town. My project is titled The Exploration of the Thiosulfate Process for the Dissolution of Gold and its Recovery via Ion Exchange. My supervisor is Professor Jochen Petersen, and my co-supervisor is Dr. Thandazilia Moyo. I will specifically be presenting on printed circuit boards and the gold that can be retrieved from this type of e-waste. In the developing world today, technological advancements have resulted in a more convenient and independent, comfortable life. However, this ever-increasing industry has generated alarming amounts of technological waste, specifically waste electric and electronic equipment, also known as e-waste. This e-waste can be subdivided into smaller categories, namely temperature exchange equipment, screens, lamps, large equipment, small equipment, and small telecommunication equipment. Printed circuit boards are a small but nonetheless key component of e-waste streams. These boards contain valuable metals such as gold and copper alongside heavy metals. Although there are various technologies currently in practice for the beneficiation of PCBs, there are certain hindrances to the growth of this sector in South Africa. PCBs are approximately 6% of the total weight of e-waste. However, this e-waste category contains the most monetary value in the e-waste sector. The value of the PCB stream is largely attributed to precious metals, primarily gold, found on the board. Considering that e-waste is one of the fastest growing waste streams in the world and the global shift towards sustainable management of resources, there is an increased need to explore recycling options for the recovery of gold found on the PCBs. A review of the typical structure of the standardized PCB indicated that all gold is found on the surface or the vias of the board and on the soldered contacts. Thus, for the purposes of this project, extensive mechanical pre-treatment of the board to expose the gold metal to solution was not required. The project focuses on the solubilization and subsequent recovery of the gold in ammonia-ammonium thiosulfate solutions. The leaching of gold in ammonia-ammonium thiosulfate solutions is an established chemistry for primary ores and will be optimized in this study. The use of ion exchange to recover gold under this process chemistry is new and represents new knowledge that will come from the study. So why ion exchange? There are many advantages and disadvantages to this method. Some of the advantages include that it is more environmentally friendly, no thermal generation is required and therefore it is energy friendly. There are higher loading capacities and loading rates associated with the ion exchange. And in comparison to other processes such as solvent extraction, it is more simple and has the potential to be automated, including the fact that it is less flammable. And when compared to activated carbon, there is better selectivity and a higher resistance to abrasion. However, there are some disadvantages for this route. Some of these include the presence of degradation products inhibiting the orothiosulfate ion absorption. Weak-based resins are not suitable due to its low gold loading ability, where gold loading ability reduces in an increasing pH from 8 to 11. The resins are slightly more expensive, and there is the potential for chemical degradation. Thus, regular replacement of the resin is required. The objectives of our project are as follows: to investigate the ammonium thiosulfate leaching system for gold recovery from printed circuit boards, and to determine the effectiveness of the ion exchange method for PCB gold recovery. Some of the key questions on my project aims to answer are as follows. What is the effect of impurities on resin performance when utilizing the PCB solutions as compared to the standardized solution containing the gold powder? What conditions are most suited for the ion exchange system in terms of gold recovery, such as temperature and speed? What other ions are found in the leach solution from PCB leaching, and what is their effect on the elution and subsequent capacity of the resin? And finally, how does the increase in background copper affect the ion exchange process? Taking a closer look at the leaching step. Standardized leach solutions are made by dissolving 99% pure gold powder in ammonia-ammonium thiosulfate solutions. The gold concentrations in these solutions are equivalent to what would have been expected if an actual standard PCB had been leached. Different background concentrations of copper were introduced into the reactors. These tests serve to validate the leaching chemistry and, more importantly, to generate pure solutions which can be used to test the ion exchange without the influence of contaminants, as well as to monitor the effect of background copper concentration on both the gold dissolution and the ion exchange process. Leach tests are then run on the actual standard PCBs, and leach solutions are analyzed to track dissolved metal concentrations. Prior to leaching, the PCBs are cut for the purposes of fitting them into the reactor and enabling agitation to minimize mass transfer limitation. Leach tests were conducted in the thermostated jacketed BSTR shown here as Figure 1 and was controlled at a temperature of 25 degrees, pH of between 9 and 10, and at 1 molar and 0.5 molar ammonia and ammonium thiosulfate concentrations, respectively. It is expected that the PCB leachate will contain trace amounts of calcium, aluminium, and iron alongside copper. The overall redox equation shows the orothiosulfate complex and the hydroxyl ion as a product. The reaction is extremely slow without the presence of cupric and ammonia. The competing effect of copper in the system can prove to have a detrimental effect on the formation of this ion. Subsequent to the leaching process is the ion exchange method. This utilizes resins in order to remove the orothiosulfate ion from the solution by attaching onto the resin. Initial tests utilize the standardized leach solutions, and these serve to validate the ion exchange process in thiosulfate systems, as well as to measure the resin capacity without the interference of contaminants otherwise expected from actual PCB leachate. The tests are then repeated using actual PCB leachate. Two types of resins are tested, as well as two types of eluents. The small clip shown on the left consists of ammonia and ammonium thiosulfate in solution, as well as the gold powder. A zero-length column, or ZLC, is utilized for these tests as it reduces complications experienced in the longitudinal dimension when using a plug flow arrangement. This is shown as Figure 4. This is essentially a small device containing the resin. This method is incorporated in a kinetics equilibrium testing as well as capacity testing, which will be expanded on in the next slide. There are three main tests that are conducted, namely capacity, kinetics, and equilibrium testing. Capacity testing is first conducted in an open circuit in order to determine the capacity of the resin in equivalents per liter, where equivalents per liter refers to the molar quantity of monovalent ions absorbed per unit volume. In this case, this type of testing, an excess amount of electrolyte is passed through the ZLC. The anionic atoms are absorbed onto the resin, and any ions present on the resin are then desorbed and collected in the effluent before being sent for analysis. The closed circuit is required for kinetics and equilibrium testing. The equilibrium testing essentially determines the equilibrium between absorbed species and species in solution. A temperature and conductivity indicator are connected to the solution. The temperature remains constant and the conductivity is recorded every 10 seconds. The kinetic testing is required in order to determine how quickly gold recovery is reached under specific conditions. This involves varying flow rates with a fixed liquid quantity contacted with the resin. This type of testing determines how much time is required for gold to be recovered for each specific resin, therefore formulating absorption isotherms for the synthetic and actual leach solutions. The outcome of this project will prove vital in playing a part in the circular economy for the recycling of e-waste. Some of the key points include the effectiveness of the thiosulfate system on gold recovery, as well as the suitable resin, eluent, and conditions for gold recovery. This project will also contribute to the development of hydrometallurgical processes that can be incorporated for the beneficiation of PCBs for high-value products. The ion exchange research and experimentation on PCB leach solutions incorporated in the project are novel components that will lay the foundation for further investigation into gold, especially in the e-waste sector. I thank you for your time, and I would like to acknowledge the following companies for their contribution to this project.